Have you ever stood in front of a building or a monument and felt your brain quietly ask, how did humans even build this? In this video, we are not just visiting the 7 wonders of the world as tourists, we are going there as engineers. From ancient stone cities hidden in the mountains to a marble mausoleum on soft river soil, every wonder hides a smart engineering trick that kept it standing for centuries. Stay till the end and tell which number on this list impressed you the most as an engineer, not just as a traveler. Number 7 on our list is a structure so long that people once joked it could be seen from space, the Great Wall of China. It is not one single wall, but layers of walls and fortifications built by different dynasties over thousands of years to slow down invasions. The real engineering problem was crazy. How do you build and maintain a defensive structure that stretches for thousands of kilometers, with no bulldozers, no trucks, and no modern cranes? Engineers did something very smart. They stopped fighting the terrain and started using it. The wall often follows ridge lines, using natural steep slopes as part of the defense, cutting material needs and making attacks harder. They built using whatever the land gave them, rammed earth in some regions, bricks and stone in others, balancing strength with local availability. Watchtowers acted like network nodes, letting soldiers send smoke or fire signals across huge distances, turning the wall into a mix of structure, road, and communication network. Number 6 is Petra, the rose-red city of Jordan, where you walk through a narrow canyon and suddenly a massive stone facade appears in front of you. That famous treasury is only the entrance to a whole city carved into rock by the Nabateans, a trading people who made the desert their home. Their biggest enemy was water, both the lack of it and the violent flash floods that could destroy everything. Engineers carved stable rock-cut buildings, but the real magic lies in the water system: channels, tunnels, cisterns, and small dams that captured rainwater and guided it safely into storage instead of through people's homes. So when you see Petra, don't just think ancient Instagram spot. Think of a combined geology, hydrology, and civil engineering project that turned rock and rain into a functioning city. Number 5 takes us to Rome, into a giant oval arena where, 2,000 years ago, crowds screamed as gladiators fought and staged battles played out on the sand. For the emperors, the Colosseum was a tool to entertain, impress, and remind everyone of Rome's power and engineering skill. From an engineering viewpoint, this is basically the world's early prototype of a modern stadium. The problem: how to move tens of thousands of people in and out safely, and give them good views, without chaos. Roman engineers built a concrete and stone bowl with arches and vaults, multiple tiers of seating, and a full network of corridors and staircases under the stands. People used numbered entrances and exits, just like gate numbers today. Below the arena floor, they designed spaces and mechanisms to move animals and scenery quickly. Modern stadiums still copy these ideas: tiered seating on structural frames, radial circulation, and planned evacuation routes. The Colosseum did it first, at massive scale. Number 4 is Chichen Itza in Mexico, where the main pyramid, El Castillo, is not just a monument but a kind of stone computer that plays with light and sound. During the equinox, the sun casts shadows that look like a serpent of light sliding down the steps to a carved snake head at the base. It feels like an ancient special effects show. The engineering challenge was to build a stable pyramid on limestone and align it precisely with the sun and stars without lasers or GPS. Engineers used stepped pyramid geometry to spread loads and oriented the structure so that only on specific days, the shadow effect appears perfectly along the staircase. There is also an acoustic trick: a clap near the staircase produces an echo that sounds similar to a bird call, thanks to the step geometry and courtyard shape. Chichen Itza shows how structural design, geotechnics, acoustics, and astronomy can all be integrated into a single piece of architecture. At number 3, we climb into the Andes to Machu Picchu, the Inca city that looks like it is glued to the top of a mountain ridge. Hidden for centuries and revealed to the outside world only in the last 100 years, it looks peaceful, but from an engineering perspective, this site is a nightmare of slopes, rain, and earthquakes. The problem: how do you build on a steep, wet, earthquake-prone ridge without the entire settlement sliding away. Inca engineers responded with terraces that doubled as farmland and as massive retaining walls, with carefully layered soil and rock to drain water instead of letting it trigger landslides. Their dry stone masonry used precisely cut blocks locked together so tightly that they can move slightly during an earthquake and then settle back without collapsing. Machu Picchu is basically a real-life lesson in slope stability, drainage, and seismic design, wrapped in stunning scenery. Number 2 brings us to India and the Taj Mahal, often called a monument of love built by Shah Jahan for Mumtaz Mahal. Most people see the white marble, the symmetry, and the reflection in the water. Engineers see something else as well, a massive load sitting on soft riverbank soil. The challenge was to keep this heavy marble structure stable for centuries next to the Yamuna River, where the ground is not naturally ideal for such weight. Builders used deep well foundations, vertical shafts sunk into the ground and reinforced, to spread loads and anchor the structure. The main dome uses a double shell concept, a strong inner dome and a taller outer dome, giving the iconic look without unnecessary extra mass. Look closely at the minarets inside shots, they are slightly leaning outward. That is intentional, so in a worst-case earthquake, they would fall away from the main tomb rather than onto it. So, behind the romantic story is a serious combination of foundation engineering, dome design, and safety thinking hidden under marble and calligraphy. Finally, number 1 on this list is Christ the Redeemer, standing with open arms above Rio de Janeiro on Corcovado Mountain. Built in the 20th century, it quickly became an icon of the city and of Brazil, visible from far away and often surrounded by clouds and storms. The engineering problem: how do you build and maintain a tall, wide-armed statue on a narrow peak that gets hammered by wind and lightning? Engineers used a reinforced concrete core to give the statue strength and flexibility, and then covered it with soapstone tiles that resist weathering and can be replaced piece by piece over time. Inside the statue there are stairs and access areas so maintenance teams can reach different parts from the inside for inspection and repair. Christ the Redeemer is a reminder that when you design a symbol on top of a mountain, you are really designing a long-term maintenance project that must survive decades of harsh conditions.